Hello everyone, I'm Shalini, student of SVCE. In this video, we will be knowing about an introduction to the fundamental concepts of vector calculus and how they help us understand the world around us. Here we have the contents: Introduction to Vector Calculus, Line Integral, Surface Integral, the gradient of a vector field, the divergence of a vector field, the curl of a vector field, applications of vector calculus, conclusion. Starting with the introduction, vector calculus is a branch of mathematics that deals with vector fields and their derivatives. Vector field is nothing but it is a function of a space whose value at each point is a vector quantity. It includes concepts like gradient, divergence, and curl, which are used to describe and analyze physical phenomena involving quantities that have both magnitude and direction. These concepts have applications in various fields such as physics, engineering, and computer graphics. It deals with two integrals such as line integrals and surface integral. Here we have line integral. In vector calculus, this is defined as the integral of some function along a curve. In simple words, it is said that a line integral is an integral in which the function to be integrated is calculated along with a curve. For example, we can also integrate a scalar valued function along a curve. Sometimes a line integral is also known as a path integral or curve integral or curvilinear integrals. Talking about surface integral, it is defined as a generalization of several integrals to the integrations over surfaces. It means that we can think about the double integral related to the line integral. For any given surface, we can integrate a scalar field over a surface or a vector field over a surface. Talking about the gradient of a vector field, here we have its definition. This points in the direction of steepest increase and as a equal magnitude to the rate of change in that direction. Here we have the example. In a temperature scalar field, the gradient at a point indicates the direction of a temperature's fastest increase, and its magnitude measures how steep that increase is. We have its applications. The gradient is used in physics, engineering, and economics to model fields that affects the behavior of particles, fluids, and markets. It also powers machine learning algorithms. Gradient can be used to specify how steep a slope can be so that it is thought as safe. Then we have other examples: a wheelchair ramp, a children's slide, a staircase. Next, talking about the divergence of a vector field, here we have its definition. If a field behaves like a source at a particular point, the vector field measures the extent to which the field behaves. Then we have the formula to find the divergence, that is del fx divided by del x plus del fy divided by del y plus del fz divided by del z. And here we have its applications. The divergence is used in fluid mechanics, electromagnetics, and more to describe the flow of fluids, the spread of heat, the movement of sound, and the behavior of waves. In general, divergence is used to study physical phenomena in three dimensions, but could theoretically be generalized to study such phenomena in higher dimensions as well. Next, we have the curl of a vector field. Here we have its definition. This measures how much the field rotates around a particular point. The curl of a vector field is a vector field. The curl of a vector field at a point P measures the tendency of particles at P to rotate about the axis that points in the direction of the curl at P. A vector field with a simply connected domain is conservative if and only if its curl is zero. Then talking about its applications, the curl is used in electromagnetics, fluid dynamics, and more to describe the movement of fluids, the behavior of electromagnetic fields, and the shape of objects. And the way to calculate the curl is as follows, that is del fz divided by del y minus del fy divided by del z into I plus del fx divided by del z minus del fz divided by del x into j plus del fy divided by del x minus del fx divided by del y into k. Then talking about the applications of vector calculus in electric field, vector calculus is used to model the flow of electric charges through a system and to calculate the electric potential and field strength at a point in space. In vector calculus notation, the electric field is given by the negative of the gradient of a electric potential, that is E is equals to minus gradient of V. This expression specifies how the electric field is calculated at a given point. Since the field is a vector, it has both direction and magnitude. Then talking about the applications of vector calculus in fluid mechanics. Vector calculus is used to describe and analyze the movement of fluids through a system and to calculate properties like pressure, velocity, and temperature. The interpretation of vector fields as fluid flow can be useful in understanding basic properties of vector fields such as divergence and curl, as well as important results in vector analysis such as Green's theorem and Stokes' theorem. And talking about its application in geometric optics, vector calculus is used to calculate the path and intensity of light as it propagates through a medium and reflects or refracts off surfaces. Geometrical optics does not account for certain optical effects such as diffraction and interference. Summing up the topics, vector calculus is a powerful tool that allows us to describe and understand the behavior of vector fields in a vast range of different settings. Its broad applicability and the computational efficiency make it a central concept in both pure and applied mathematics and in many other fields of science and engineering. Thank you.